Picture this. You're pushing a shopping cart and it gets heavier the faster you go. Not because you're adding items, because speed itself adds weight. Sounds insane, right? But that's exactly what happens when you approach light speed. The faster you move, the more massive you become, until reaching light speed would require infinite energy. But here is the terrifying question. What if you could break that rule? What if something with mass actually reached the speed of light? Consequences wouldn't just be dramatic, they could unravel the very fabric of reality itself. Are you ready to find out why? Let's begin. First, let's talk about what infinite mass means. Mass isn't just weight. Mass warps space-time. That's what gravity is, the bending of space and time around massive objects. Earth curves space-time just enough to keep you on the ground and the moon in orbit. The sun curves it more, holding 8 planets in a cosmic dance. Black holes curve it so much that not even light escapes. Now imagine something with infinite mass, infinite curvature, infinite gravitational pull. The moment an object reached light speed, space-time around it wouldn't just bend, it would collapse. The gravitational field would become so intense that it might create a singularity, a point where the laws of physics break down completely. Think of it like this. Black holes form when massive stars collapse because their gravity becomes too strong to resist. But those stars had finite mass. Our hypothetical light-speed object has infinite mass. What forms when infinite mass concentrates in one spot? We don't know. The equations literally give us infinity as an answer, which in physics is usually nature's way of saying this scenario is impossible, but if it happened, you'd essentially create an instant black hole of unlimited power, not just a black hole that swallows light, a black hole that might swallow space-time itself. And here's where it gets worse. This object isn't sitting still, it's moving at light speed. That means this infinitely massive space-time shredding singularity is plowing through the universe at the maximum possible velocity. Every atom it passes, every particle of dust, every photon in its path would experience a collision with infinite energy. Let's pause on that word, infinite. Not a lot, not more than anything we've seen. Infinite, unlimited, boundless. Every collision would release energy without limit. The smallest speck of matter touched by this object would trigger an explosion that makes supernovae look like birthday candles. A supernova, the death explosion of a massive star, releases about 10 to the 44th joules of energy. That's a 1 followed by 44 zeros, enough to outshine an entire galaxy for weeks. The collision we're describing would make that look like nothing, because infinity isn't just bigger than big numbers, it's categorically different. It's beyond comparison. But energy release is just the beginning of our problems. Let's talk about what happens to time itself. According to relativity, time is not absolute. It flows differently depending on how fast you're moving. This isn't theory anymore, it's measured fact. GPS satellites have to correct for time dilation because they orbit Earth at high speeds. Astronauts on the International Space Station age slightly slower than people on the ground. These effects are tiny at normal speeds, but they grow dramatically as you approach light speed. At light speed, time dilation becomes infinite. From the perspective of a photon traveling across the universe, zero time passes. The photon is emitted and absorbed in the same instant from its point of view. The entire 13.8 billion-year history of the universe happens in a frozen moment. Now put a massive object in that state. What does that mean? Does it experience time? Can it interact with anything? Does causality, the relationship between cause and effect, still function? Here's where physics starts screaming in protest. Cause and effect depend on time flowing forward. You can't have an effect before a cause, but at light speed, past, present, and future might become meaningless concepts. The object would exist in a state where it simultaneously hasn't started moving yet and has already reached its destination. It would be everywhere along its path at once, from a certain perspective. This breaks causality. And when causality breaks, the universe stops making sense. Imagine you're watching a movie, but someone scrambles the scenes. The ending plays before the beginning. The hero dies before the villain attacks. The universe solves problems before they happen. That's what a universe without causality looks like. And an object traveling at light speed might create exactly that chaos. Let's dig deeper into why this matters. In our everyday experience, time moves forward in one direction. You drop a glass, then it shatters. You don't see shattered glass spontaneously reassemble and leap into your hand. This arrow of time, this forward flow, is built into the fabric of reality. It's connected to entropy, to the second law of thermodynamics, to the way information spreads through the cosmos. But relativity tells us something strange. The faster you move, the more your experience of time differs from everyone else's. If you're moving towards something, time appears to speed up for that object. If you're moving away, time slows down. At normal speeds, these effects are unnoticeable, but at light speed, they become extreme. If you're enjoying this mind-bending journey through physics, hit that subscribe button and give this video a thumbs up. It helps more people discover these cosmic mysteries. And I'd really appreciate your support as this channel grows. Your curiosity fuels this content. From the perspective of our impossible light speed object, the entire universe ahead of it would be blue shifted into oblivion. Blue shift happens when light waves compress because you're moving toward their source. At light speed, this compression becomes infinite. Every wavelength of light, every radio wave, every microwave photon in front of you would be compressed down to infinite energy. That means the cosmic microwave background, the gentle afterglow of the Big Bang that bathes the universe in a temperature of about 3 degrees above absolute zero, would transform into a wall of infinitely energetic radiation. The starlight ahead would become gamma rays of unlimited power. You wouldn't be traveling through empty space. You'd be plowing through an infinite energy barrier. And here's the truly terrifying part. You'd be creating that barrier. The universe doesn't normally work this way, but your impossible speed would transform ordinary space into a weapon against you and against everything else. Think of it like a shockwave. When a plane breaks the sound barrier, it creates a sonic boom because air molecules can't get out of the way fast enough. The plane compresses them into a pressure wave that ripples outward. Now imagine breaking not the sound barrier, but the cosmic speed limit itself. You'd create a shockwave in space-time, a rupture in the fabric of reality. Physicists have a name for something similar: Cherenkov radiation. When particles move through a medium faster than light can move through that same medium, they emit a blue glow. You've seen this if you've ever looked at photos of nuclear reactors. That eerie blue light in the water is Cherenkov radiation from particles zipping faster than light can travel through water. They're not breaking the universal speed limit, just the local one for that particular medium. But what if you could move at light speed through the vacuum of space itself? Some theoretical physicists have explored what might happen. You might create Cherenkov radiation in the fabric of space-time. Not light, not particles, a radiation of reality itself, a wake of destabilized space and time rippling out behind you. This destabilization wouldn't just be local. Remember, we're dealing with infinite energy and infinite mass. The effects would propagate, they would spread. And depending on how space-time responds, that spreading could be catastrophic. Here's an analogy. Imagine reality is like a frozen lake. Most of the time, it's stable. You can walk on it, skate on it, even drive a car across it if it's thick enough. But if you hit it hard enough in just the right way, you create a crack. And that crack spreads. What starts as a small fracture can spiderweb across the entire surface until the whole thing collapses. Our light-speed object might crack space-time itself. And once that crack starts, where does it stop? This brings us to one of the most terrifying concepts in modern physics: vacuum decay. The vacuum of space isn't actually empty. It's filled with quantum fields that permeate every cubic centimeter of the universe. These fields have energy states, like a ball resting in a valley. Our universe exists in what physicists call a vacuum state, a particular energy level of these fields. But here's the unsettling part. We're not entirely sure if our vacuum is the lowest energy state possible. It might be what's called a false vacuum, a temporary stable state that could, under the right conditions, decay into a lower energy true vacuum. If that happened, it would release enormous amounts of energy and fundamentally change the laws of physics in the affected region. Think of it like a supercooled liquid. Water can sometimes remain liquid below its freezing point if it's perfectly still. But the moment you disturb it, tap the container, drop in a seed crystal, it instantly crystallizes. The entire volume transforms in a flash. Vacuum decay would work similarly. One tiny region transforms, and that transformation spreads at the speed of light in an expanding bubble. Everything inside the bubble operates under different physical laws. Atoms might not hold together anymore. The forces that govern chemistry and biology could cease to function. We have no evidence this is happening, and most physicists think our vacuum is probably stable, but an object traveling at light speed, carrying infinite energy, creating infinite space-time curvature? That might be exactly the kind of disturbance that could trigger vacuum decay. You wouldn't just destroy yourself, you'd potentially unleash a transformation wave that rewrites the rules of physics across the entire universe, and there's no stopping it once it starts. The bubble expands at light speed, no warning, no escape, no defense. Galaxies billions of light years away would be fine for billions of years, until one day the bubble reaches them and reality simply changes. If you're wondering more about why the universe has this speed limit in the first place, and what deeper principles Einstein and Feynman uncovered, I actually made a detailed video exploring exactly that. It's called "Why is Light Speed the Limit? What Feynman Uncovered Will Melt Your Mind." I break down the fundamental reasons behind this cosmic boundary and why it's not just a speed limit, but a protection mechanism for reality itself. You'll find it really complements what we're discussing here. Check it out after this one. The link is in the description and on the card above. But let's continue with our catastrophe scenario. We've talked about infinite energy, space-time collapse, causality breakdown, and vacuum decay. Now let's discuss what happens to the object itself. You are made of atoms. Atoms are mostly empty space. The nucleus is tiny compared to the electron cloud around it, but those electrons are held in place by electromagnetic forces. The protons and neutrons in the nucleus are bound together by the strong nuclear force. These forces have specific strengths, specific ranges, specific rules. As you accelerate toward light speed, relativistic effects don't just change your mass. They change how forces work in your reference frame. The electromagnetic force that holds your atoms together experiences what's called relativistic beaming. From your perspective, forces ahead of you intensify while forces behind you weaken. At light speed, this becomes infinite. Your own atomic structure would experience infinite stress. The forces that hold you together would be torn between infinite compression ahead and infinite stretching behind. You wouldn't just disintegrate, you'd cease to exist as a coherent object. Every particle that makes up your body would be ripped into a state that physics can barely describe. Some physicists have joked that approaching light speed would turn you into a pancake because length contraction would compress you in the direction of motion. But at actual light speed, there's no pancake. There's no you. There's just a singularity of infinite energy leaving a trail of broken space-time. And let's not forget about the path you're traveling. Space isn't actually empty. There's about 1 hydrogen atom per cubic centimeter in the space between stars. That doesn't sound like much, but when you're traveling at light speed, you're hitting over 10 to the power of 17 atoms every second. That's 100,000 trillion atoms per second. Each collision releases infinite energy. Each one creates its own miniature catastrophe. The hydrogen atoms don't just get pushed aside, they experience a collision with infinite momentum, infinite kinetic energy, infinite force. They would be accelerated to unimaginable energies themselves, creating cascading particle reactions that spread outward from your path like a cosmic wildfire. Let's zoom into one of those collisions. A single hydrogen atom floating peacefully in the void between stars. It's been drifting there for millions of years, maybe billions. Then suddenly our impossible light-speed object slams into it. From the hydrogen atom's perspective, it doesn't see you coming. Information about your approach can only travel at light speed, and you're matching that speed. There's no warning, no advance notice. One moment, everything is calm. The next moment, infinite energy impacts it. The atom doesn't just split. Nuclear fission, the splitting of atomic nuclei, releases energy measured in millions of electron volts. The collision we're describing operates on an entirely different scale. The proton and electron don't separate cleanly. They're subjected to forces so extreme that they might break down into their constituent quarks. And those quarks experience conditions that only existed in the first trillionth of a second after the Big Bang. When quarks are compressed to incredibly high energies and densities, they enter a state called quark-gluon plasma. This isn't regular matter, it's a soup of fundamental particles where protons and neutrons can't even form. The early universe existed in this state before it cooled enough for atoms to exist. Particle physicists at CERN and the Brookhaven National Laboratory have created tiny amounts of quark-gluon plasma by smashing heavy nuclei together at 99.99% light speed. But our collision involves infinite energy. What state of matter forms under infinite pressure and infinite temperature? Physics doesn't have an answer. The equations break down. We've exceeded the limits of our understanding. And remember, this isn't happening to one atom. It's happening to every atom in your path. You're creating a trail of subatomic destruction stretching across the cosmos, a line of broken matter where the fundamental building blocks of reality have been shattered. But the damage doesn't stay confined to your path. Energy radiates outward from collision sites. At these extreme energies, you'd produce what physicists call secondary particles, new particles created from pure energy. High-energy cosmic rays that hit Earth's atmosphere do this on a small scale. One cosmic ray proton smashes into an air molecule and creates a shower of thousands or millions of secondary particles that cascade down through the atmosphere. Your collisions would create something far worse. The secondary particles would themselves carry enormous energy. They'd shoot outward in all directions, striking other atoms, creating tertiary particles, then quaternary particles, spreading like a nuclear chain reaction, but across light years of space instead of kilograms of uranium. This cascade wouldn't stop, it would grow. Each generation of particles would trigger more collisions, more energy release, more destruction. You'd essentially create an expanding sphere of chaos centered on your path. And because some of these secondary particles would also be traveling near light speed, the sphere would expand almost as fast as you're moving. Now let's think bigger. Let's think about what your journey does to the structure of space itself. Einstein's general relativity tells us that mass and energy warp space-time. This isn't just a mathematical abstraction, we've measured it. We've seen starlight bend around the sun during eclipses, exactly as Einstein predicted in 1915. We've detected gravitational waves, ripples in space-time created by colliding black holes billions of light-years away. The LIGO Observatory picked up these signals in 2015, confirming a prediction Einstein made a century earlier. Gravitational waves travel at light speed. They're distortions in space-time that propagate outward like ripples on a pond. When two black holes spiral into each other, they create gravitational waves so powerful we can detect them across the observable universe. The black holes involved in that first detection were about 30 times the mass of our Sun each. Now imagine the gravitational disturbance created by an object with infinite mass. It wouldn't create waves, it would create a tsunami, a catastrophic deformation of space-time that spreads outward at light speed, warping the fabric of reality in its wake. Here's what makes this truly terrifying. Gravitational effects propagate at light speed, but you're also traveling at light speed. That means you're keeping pace with your own gravitational disturbance. Normally, when something massive moves, it creates gravitational waves that spread outward and dissipate. But if you're moving at the same speed as those waves, they can't escape ahead of you. They pile up, they amplify. It's called wave interference. When waves overlap, they can add together. Imagine throwing two stones into a pond. Where the ripples meet, they create patterns of reinforcement and cancellation. But you're not throwing two stones. You're continuously generating waves while moving at exactly their propagation speed. The result would be a buildup of gravitational distortion ahead of you that grows without limit. This phenomenon has a parallel in sound. It's why sonic booms exist. Sound waves pile up at the front of a supersonic aircraft because the plane is moving faster than the waves can propagate. The result is a shock wave, a sudden, intense pressure change. What you'd create is a gravitational shock wave, a discontinuity in space-time itself. And where that shock wave passes, the geometry of space would change so dramatically that matter might not be able to exist in its current form. Think about what holds matter together. Atoms exist because electrons orbit nuclei at specific distances, governed by quantum mechanics and electromagnetic forces. But those forces operate in space-time. They depend on space having certain properties, 3 dimensions, specific curvature, predictable geometry. If space-time becomes wildly distorted, those properties change. The distance between an electron and its nucleus might suddenly fluctuate. The strength of the electromagnetic force might vary across tiny regions of space. Quantum mechanics assumes a smooth, continuous space-time. What happens when space-time becomes chaotic and discontinuous? Atoms might simply cease to function. The electron orbitals that allow chemistry to exist might become unstable. Molecules could fall apart not because they're hit by something, but because the underlying framework that allows them to exist has been damaged. This is destruction at a level beyond anything we've encountered. We know about explosions. We understand nuclear weapons, supernovae, even gamma-ray bursts, the most energetic explosions in the universe, which release more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. But those events destroy matter by hitting it, by transferring energy to it. What we're describing is the destruction of the stage on which matter exists. Not breaking the actors, but collapsing the theatre itself. And there's another problem we haven't addressed: information. In physics, information is physical, it's not abstract. When particles interact, they exchange information. When light travels from a star to your eye, it carries information about that star's temperature, composition, motion. The universe is constantly processing information through every interaction, every quantum event, every particle collision. Information is also conserved according to fundamental principles. It can't be destroyed only transformed or spread out. This is why black holes created such a controversy. Stephen Hawking argued in the 1970s that black holes destroy information, which would violate conservation laws. The debate raged for decades until physicists developed theories suggesting that information is preserved in subtle ways, perhaps encoded on the black hole's event horizon. But our light-speed object presents a new information paradox. When you're traveling at light speed, you experience zero time. From your perspective, your journey is instantaneous. You exist at your starting point and your destination simultaneously. But information can't propagate faster than light. So how does information about your starting conditions transfer to your destination if, from your perspective, no time passes? And what about the information contained in all the atoms you're destroying? Each hydrogen atom has a quantum state, a specific configuration of properties like spin, position, momentum. When you obliterate that atom with infinite energy, where does that information go? Does it spread into the secondary particles? Does it get encoded in the space-time distortions you create? Or does it simply vanish, violating one of physics' most fundamental principles? If information is destroyed, we have a problem bigger than just this one event. The laws of quantum mechanics depend on information conservation. If that law can be broken, then the foundation of our understanding collapses. Quantum mechanics governs everything from the behavior of atoms to the fusion reactions in stars to the formation of galaxies. Without it, we can't predict how matter behaves. A universe where information can be destroyed is a universe where cause and effect become unreliable, where the past doesn't determine the future, where identical starting conditions can lead to different outcomes for no reason, where the very concept of physical law becomes meaningless. You see, the universe isn't just a collection of stuff moving through space, it's a vast information processing system. Every interaction, from electrons changing energy levels to galaxies colliding, involves the transfer and transformation of information. That's what makes the universe comprehensible, predictable, governed by laws rather than chaos. Our light-speed object would corrupt that information flow. It would create regions where information is destroyed, duplicated, or scrambled beyond recovery. And those regions would spread, infecting larger and larger volumes of space with informational chaos. Let's talk about fields. Not the kind you plant crops in, but the invisible fields that fill every point in space throughout the entire universe. These fields are fundamental to how reality works, and our light-speed object would wreak havoc on all of them. The electromagnetic field is everywhere. Right now, electromagnetic waves are passing through your body, radio waves from stations broadcasting miles away, microwaves from cell towers, infrared radiation from warm objects around you, visible light from the sun or your screen. The electromagnetic field connects every charged particle in the universe to every other charged particle. When you flip a light switch, electrons start moving in the wire, and that movement creates a disturbance in the electromagnetic field that propagates outward at light speed. This field has a resting state, a baseline energy level, but it's never truly still. Quantum mechanics tells us that even in a perfect vacuum, the electromagnetic field fluctuates. Virtual particles pop in and out of existence. Photons appear briefly and then vanish. This isn't science fiction. These quantum fluctuations have measurable effects. They cause the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny attractive force because the fluctuations between them are restricted compared to the fluctuations outside. The Lamb shift, discovered in 1947, showed that these vacuum fluctuations actually change the energy levels of electrons in hydrogen atoms. Physicists at Columbia University measured this effect with incredible precision, confirming that the quantum vacuum isn't empty, it's seething with activity. Now imagine what happens when an object with infinite energy plows through this delicate quantum field structure. The electromagnetic field doesn't just get disturbed, it gets torn apart. The baseline state becomes unstable. The virtual particles that normally flicker in and out of existence might get ripped into real particles by the extreme energy density, or the field itself might transition into a completely different state, one where the rules governing light, electricity, and magnetism no longer work the way they do now. In regions where the electromagnetic field is destabilized, atoms can't exist. Chemistry becomes impossible. The forces that allow molecules to form, that allow DNA to encode information, that allow stars to shine and planets to hold together, all of these depend on the electromagnetic field behaving predictably. And the electromagnetic field is just one of several fundamental fields. There's also the Higgs field, which gives particles their mass. The discovery of the Higgs boson at CERN in 2012 confirmed that this field exists. Particles interact with the Higgs field as they move through space, and that interaction is what we experience as mass. Different particles interact differently. Electrons barely interact at all, so they have very little mass. Quarks interact more strongly, so they're heavier. But what if the Higgs field gets disrupted? What if our light-speed object's infinite energy causes the Higgs field to shift into a different state? Suddenly particles might have different masses than they did before. Electrons might become heavier, quarks might become lighter. The delicate balance that allows protons and neutrons to form, that determines which elements can exist, would be completely rewritten. You might end up with a region of space where hydrogen atoms are impossible because the changed masses make them unstable. Where carbon, the foundation of all known life, simply cannot exist. Where the nuclear fusion processes that power stars shut down because the physics no longer allows them. This isn't abstract speculation. We know fields can have multiple stable states. We know that transitions between these states can happen. We've even created tiny, controlled field transitions in laboratory settings. What we don't know is what happens when you hit these fields with infinite energy while moving at light speed through them. The strong nuclear force field might also be affected. This is the field that holds quarks together inside protons and neutrons. It's described by quantum chromodynamics, one of the most successful theories in physics. The strong force is incredibly powerful but operates only over incredibly tiny distances, about 10 to the minus 15 meters, roughly the size of a proton. When you try to pull quarks apart, the strong force actually gets stronger, like a rubber band that resists more the farther you stretch it. This is called confinement. It's why we never see individual quarks in nature. They're always bound together in groups. But extreme energy densities can overcome confinement. That's what creates quark-gluon plasma. In the conditions we're describing, you might not just create small pockets of quark-gluon plasma. You might destabilize the strong force field across large regions of space. Protons and neutrons would dissolve. Atomic nuclei would cease to exist. Matter would revert to a primordial state that hasn't existed in the universe since fractions of a second after the Big Bang. And unlike the early universe, where everything was uniformly in this state and then cooled smoothly, you'd have a chaotic boundary between normal matter and dissolved matter. A front where reality as we know it simply stops working, spreading outward at light speed. Now let's consider quantum entanglement. This is one of the strangest phenomena in physics. When two particles become entangled, measuring a property of one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seemed to violate his principle that nothing can travel faster than light. But entanglement doesn't actually transmit information faster than light. It's more subtle than that. The particles share a quantum state, and measuring one collapses that shared state for both. Physicists have confirmed entanglement over distances of hundreds of kilometers. China's Michus satellite created entangled photons and sent them to ground stations over 1,000 kilometers apart in 2017, maintaining the entanglement across that vast distance. Entanglement is fragile, though. It's easily disrupted by interactions with the environment. That's why quantum computers are so hard to build. Maintaining entanglement long enough to perform calculations requires isolating quantum bits from any outside interference. The universe is actually full of entanglement. Particles that interacted in the past often remain entangled. Some physicists think entanglement might be fundamental to how spacetime itself is structured. The ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, suggests that quantum entanglement and wormholes in spacetime might be the same phenomenon viewed from different perspectives. If that's true, then disrupting entanglement doesn't just affect individual particle pairs, it might affect the structure of spacetime itself. Our light-speed object, creating infinite disturbances across space, would shred entangled states throughout enormous regions. If entanglement really does underlie spacetime geometry, you'd be tearing holes in the fabric of space at a fundamental quantum level. This brings us to a deeply unsettling possibility. The breakdown might not stay local. Quantum mechanics is non-local by nature. Entangled particles affect each other across arbitrary distances. If you disrupt entanglement on a massive scale, the effects might propagate through the web of entangled particles faster than normal causality allows. Imagine the universe as a vast network where distant points are connected by invisible threads of entanglement. You're not just cutting a few threads, you're shredding millions, billions, uncountable numbers of these connections. The network doesn't just develop a few holes, it starts to collapse. And because entanglement connects particles across light years of space, the collapse might not respect the normal light speed limit on cause and effect. Information about the collapse could potentially spread through the entanglement network in ways that seem to violate causality. Not because anything is actually traveling faster than light, but because the web itself exists outside normal space in a certain sense. This gets into some of the deepest mysteries of quantum mechanics. The measurement problem, wave function collapse, the nature of quantum states before they're observed. These are questions physicists have debated for a century. We don't fully understand what measurement means in quantum mechanics, or whether the wave function represents something physically real or just our knowledge of a system. But whatever measurement is, whatever wave functions represent, our light-speed catastrophe would create a situation where the normal rules don't apply. You'd have regions where quantum superposition breaks down entirely, where wave functions can't collapse properly, where the probabilistic nature of quantum mechanics gives way to complete unpredictability, not because we lack information, but because the underlying quantum structure has been damaged. Let's zoom out and think about cosmic structure, galaxies, stars, planets. These exist because the universe has structure at every scale. That structure formed over billions of years through gravitational attraction. Tiny variations in density in the early universe grew over time. Denser regions attracted more matter, becoming denser still. Eventually, these regions collapsed into the first stars, which formed the first galaxies, which merged and evolved into the cosmic web we see today. The Hubble Space Telescope, the James Webb Space Telescope, launched in 2021, and ground-based observatories have mapped this structure in exquisite detail. We can see galaxies stretching back to when the universe was only a few 100 million years old. We can trace how structure evolved over 13.8 billion years of cosmic history, but that structure depends on spacetime being stable. Gravity works because spacetime curves in predictable ways around mass. Orbits are stable because the geometry of space remains consistent. The Earth orbits the Sun in an ellipse because spacetime around the Sun has a particular shape that doesn't change randomly. Our light-speed object would destabilize that geometry. As it passes through a galaxy, the space-time distortions it creates would disrupt gravitational fields. Stars orbiting the galactic center might find their orbits suddenly changed. Some would be flung outward into intergalactic space. Others would spiral inward, creating a cascade of collisions near the galactic core. Planets orbiting those stars would be torn from their orbits. Some would be ejected into the cold darkness between stars. Others would plunge into their suns. Binary star systems would break apart. Globular clusters, dense collections of hundreds of thousands of stars orbiting galaxies, would dissolve into chaos. And this would all happen not over millions of years, but in an instant. The gravitational shockwave would rip through stellar systems faster than light could travel from one star to another within those systems. Planets wouldn't see it coming. One moment, stable orbit. The next, ejected into the void or falling toward annihilation. But what about the most extreme objects in the universe? What happens when our impossible light-speed traveler encounters a black hole? Black holes are regions where space-time curvature becomes so extreme that nothing can escape. Not light, not matter, not information, at least according to classical general relativity. The boundary of a black hole is called the event horizon. Cross that boundary and every possible future path leads inward to the singularity at the center, where density becomes infinite and physics breaks down. We've detected dozens of black holes through their effects on nearby matter. A supermassive black hole at the center of our Milky Way galaxy, called Sagittarius A star, has a mass of about 4 million times that of the Sun. We've watched stars orbit around this invisible monster, their motion revealing its presence. In 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole's shadow, the supermassive black hole at the center of the M87 galaxy, 65 million times more massive than our Sun. Black holes are already places where our understanding of physics is pushed to its limits. So what happens when something with infinite mass and infinite energy collides with one? First, consider the approach. Black holes don't just sit there quietly. They warp space-time around them dramatically. Time flows slower near a black hole. If you watch someone fall toward an event horizon from a safe distance, you'd see them slow down, their image getting more and more red-shifted, appearing to freeze just at the horizon. From their perspective, they'd cross the horizon in finite time and continue falling toward the singularity. But you're traveling at light speed, you're not falling in slowly, you're slamming into the black hole at maximum velocity, and you have infinite mass yourself. So what happens when infinity collides with infinity? Mathematics doesn't handle this well. Infinity plus infinity is still infinity, but infinity times infinity creates problems even in mathematics. When physicists encounter infinities in their equations, it usually means the theory has reached its limits. General relativity gives us infinities at black hole singularities, which tells us we need a theory of quantum gravity to describe what really happens there. But we don't have a complete theory of quantum gravity yet. String theory, loop quantum gravity, and other approaches are still being developed. We can make educated guesses based on what these theories suggest, but we're in uncharted territory. One possibility: the two infinities don't simply add together. They might create a larger black hole, one that contains the mass energy of both the original black hole and your infinite mass. But how do you create a black hole bigger than infinite? The question doesn't even make sense. Another possibility: the collision might be so violent that it tears apart the event horizon itself. Black holes have rules encoded in the laws of black hole thermodynamics. They have temperature, entropy, and information content related to the surface area of their event horizons. Stephen Hawking showed in 1974 that that black holes actually emit radiation due to quantum effects near the horizon, Hawking radiation. Given enough time, this radiation would cause a black hole to evaporate completely. But Hawking radiation is incredibly slow for large black holes. A solar mass black hole would take 10 to the 67th years to evaporate, far longer than the current age of the universe. Supermassive black holes would take even longer. Your collision wouldn't wait for slow evaporation. You'd hit the event horizon with infinite kinetic energy. Hawking radiation is caused by quantum fluctuations right at the horizon, where virtual particle pairs are separated by the black hole's gravity. One particle falls in, the other escapes. The process is delicate and subtle. Your impact would be neither delicate nor subtle. You'd dump infinite energy into the quantum fields at the horizon. The particle production wouldn't be a slow trickle, it would be an explosion. The event horizon might undergo what physicists call a firewall event, a sudden, catastrophic release of energy that incinerates anything approaching. The black hole firewall hypothesis was proposed in 2012 by physicists Joseph Polchinski, Ahmed Almheiri, Donald Maroff, and James Sully. They argued that preserving quantum information in black hole evaporation might require the event horizon to be a high-energy wall rather than the smooth boundary general relativity predicts. The hypothesis sparked intense debate that continues today. But whether or not normal black holes have firewalls, yours certainly would. The energy release would be unbounded, and it wouldn't stay contained near the event horizon. It would propagate outward as radiation and particles moving at or near light speed. The black hole would become a beacon of destruction, irradiating everything around it with enough energy to vaporize stars. And remember, black holes spin. When matter falls into a spinning black hole, it can extract rotational energy through a process called the Penrose process, described by physicist Roger Penrose in 1969. Rotating black holes drag space-time around with them, creating a region called the ergosphere, where space itself is pulled along with the black hole's rotation. Your collision with a rotating black hole would involve these rotational effects at infinite intensity. The space-time dragging would become extreme. The frame dragging effect, which is tiny and subtle for normal black holes, would amplify beyond anything describable. Space-time wouldn't just twist. It might wind itself into knots, creating closed time-like curves, paths through space-time that loop back on themselves, potentially allowing time travel. Time travel creates paradoxes. The famous grandfather paradox. If you go back in time and prevent your grandfather from meeting your grandmother, you're never born, so you never go back in time, so your grandparents do meet, so you are born, and the loop continues. Physicists have proposed various solutions to time travel paradoxes, from parallel timelines to the self-consistency principle, which states that only non-paradoxical time travel is possible. But our scenario isn't about a person carefully traveling back in time with a time machine. It's about space-time becoming so twisted that causality simply breaks. Events might cause themselves. Effects might precede their causes not by someone's choice, but because the geometric structure of space-time has become so distorted that the concepts of before and after lose meaning. And if causality breaks in one region, does it stay broken? Or does the breakdown spread? If an effect can precede its cause in one location, that might trigger effects in other locations that also precede their causes. Causality violation might be contagious, spreading through space-time like a virus, infecting cause and effect relationships throughout the cosmos. Let's consider another extreme object, a neutron star. These are the collapsed cores of massive stars that exploded as supernovae. A neutron star packs about 1.4 times the Sun's mass into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The surface gravity is so intense that if you dropped an object from 1 meter above the surface, it would hit at millions of meters per second. Neutron stars are held up by neutron degeneracy pressure, a quantum mechanical effect where neutrons resist being squeezed into the same state. This pressure is what prevents the star from collapsing into a black hole, but it's a delicate balance. Add too much mass, and the star does collapse, forming a black hole. When our light-speed object hits a neutron star, it doesn't just add mass, it adds infinite mass instantly. The neutron degeneracy pressure doesn't stand a chance. The entire star would collapse to a black hole in a fraction of a second, but not a normal collapse. This would be a collapse loaded with infinite energy. The explosion would make normal supernovae look tiny. A typical supernova releases about 10 to the 44th joules, enough to outshine an entire galaxy temporarily. The most energetic supernova we've observed, called hypernovae, release about 10 times more energy. Gamma-ray bursts, likely produced when massive stars collapse directly to black holes, are even more energetic, releasing up to 10 to the 47th joules. Your neutron-star collision would dwarf all of these. The energy release would be unbounded. The explosion would propagate outward at light speed, carrying enough energy to vaporize any planet, any star, any object in its path. And because the energy is infinite, the explosion wouldn't dissipate with distance the way normal explosions do. The intensity wouldn't follow an inverse square law. It would remain catastrophically destructive across light years, possibly across the entire galaxy. Magnetars are a special type of neutron star with magnetic fields 1,000 trillion times stronger than Earth's. These fields are so intense they distort the shapes of atoms, making chemistry impossible on the magnetar's surface. Occasionally, magnetars undergo starquakes, sudden shifts in their crusts that release enormous bursts of gamma rays and X-rays. In 2004, a magnetar called SGR 1806-20 flared, releasing in 1/10 of a second more energy than our Sun produces in 100,000 years. The burst of radiation partially ionized Earth's upper atmosphere from 50,000 light-years away. It was the largest explosion ever detected from an object outside our solar system. Now imagine that magnetar hit by infinite energy. The magnetic field wouldn't just intensify, it would undergo a catastrophic transformation. Magnetic field lines, which normally organize neatly around the star, would tangle and snap. Each snap would release devastating amounts of energy. The magnetar would become an electromagnetic catastrophe, sending out pulses of radiation so intense they'd strip electrons from atoms across parsecs of space. These pulses would interact with the electromagnetic fields throughout nearby space, inducing currents, creating secondary bursts, triggering chain reactions in any other magnetized objects they encountered. The electromagnetic chaos would spread, creating a region where magnetic fields fluctuate wildly, where any object with magnetic properties becomes unstable, where the smooth electromagnetic field structure, essential for normal physics, is shredded into incoherence. Let's step back and consider something even more mysterious: dark matter. We know it exists because we can see its gravitational effects, but we've never directly detected a dark matter particle. Galaxies rotate too fast for the visible matter we see, stars, gas, dust, to hold them together. The gravity from visible matter alone isn't enough. There must be something else, something that doesn't emit or absorb light, providing additional gravitational pull. Observations of galaxy clusters show the same thing. The Bullet cluster, formed by the collision of two galaxy clusters, provides some of the best evidence for dark matter. Astronomers observed in 2006 that the visible matter in hot gas was separated from the gravitational center of mass, which remained with the galaxies themselves. The only explanation that fits the observations is invisible matter passing through the collision while the gas interacted and slowed down. Dark matter makes up about 85% of all matter in the universe. It outweighs normal matter by about 5 to 1. We're surrounded by it. It's passing through you right now. Billions of dark matter particles every second, interacting so weakly with normal matter that you never notice. But what is it? The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that only interact through gravity and possibly the weak nuclear force. They'd be heavy, much heavier than protons, but incredibly elusive. Physicists have built elaborate detectors deep underground, shielded from cosmic rays, waiting to catch the rare event when a dark matter particle actually collides with a normal atom. So far, no confirmed detection. Dark matter remains mysterious. We know it's there, we know roughly how much there is, we know how it's distributed throughout the universe, but we don't know what it's made of. Now, what happens when our light-speed object passes through regions filled with dark matter? If dark matter particles barely interact with normal matter, do they interact with our impossible object? And if so, what are the consequences? Here's where things get strange. Dark matter doesn't interact electromagnetically, that's why it doesn't shine, but it does interact gravitationally, and our object has infinite mass, creating infinite gravitational pull. Dark matter in the vicinity wouldn't just be attracted, it would be ripped from its normal distribution and dragged along with devastating force. Dark matter provides the gravitational scaffolding that holds galaxies together. It's distributed in halos around galaxies extending far beyond the visible matter. These halos are what keep galaxies from flying apart despite their rapid rotation. If you suddenly remove or redistribute dark matter, gravitational equilibrium collapses. Your path through a galaxy would create a trail where dark matter has been violently displaced. The gravitational structure holding the galaxy together would be disrupted along that line. Stars and gas clouds would find themselves in regions where gravity suddenly doesn't match what it was moments before. Orbits would destabilize, the galactic disk might begin to warp or fragment. Over thousands or millions of years, the galaxy might tear itself apart, unable to maintain cohesion without its dark matter foundation. And unlike the visible destruction we've described, this damage would be invisible. You couldn't see the dark matter displacement with telescopes. You'd only notice the consequences later, when stars start behaving strangely, when galaxies begin to distort and dissolve for no apparent reason. But dark matter might not be the strangest thing affected. Let's talk about dark energy. Dark energy is even more mysterious than dark matter. It makes up about 68% of the total energy content of the universe. While dark matter pulls things together through gravity, dark energy pushes things apart. It's causing the expansion of the universe to accelerate. Astronomers discovered this in 1998 when studying distant supernovae. Two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, independently found that supernova billions of light-years away were dimmer than expected. The only explanation that fit was that the universe's expansion is speeding up, not slowing down. Something is pushing space apart, and that something is dark energy. We don't know what dark energy is. The simplest explanation is that it's the energy of empty space itself, the cosmological constant that Einstein introduced in 1917 and later called his biggest blunder. Quantum field theory predicts that empty space should have energy, but the predicted value is about 10 to the 120 times larger than what we observe. That's not just wrong, it's spectacularly wrong, maybe the worst prediction in the history of physics. Yet dark energy is definitely real. It's accelerating cosmic expansion. Galaxies are moving away from each other faster and faster. Eventually, in hundreds of billions of years, distant galaxies will recede so fast that light from them will never reach us. The observable universe will shrink. Galaxies outside our local group will disappear beyond a cosmic horizon. Now here's the terrifying question. What happens if your light speed catastrophe affects dark energy? If dark energy is a property of space itself and you're tearing space apart, does dark energy become unstable? Does its density change? Does it transition into a different state? If dark energy increases in regions you've passed through, those regions would expand faster than the rest of the universe. Space itself would stretch more rapidly. Galaxies in those regions would be pushed apart. Eventually, even galaxies bound by gravity would be torn apart. Then solar systems, then planets, then molecules, then atoms. This is the Big Rip scenario, a hypothetical end to the universe, where accelerating expansion eventually tears everything apart. Normally, physicists think the Big Rip would only happen if dark energy has certain specific properties, and observations suggest it probably doesn't. The universe is more likely headed for a big freeze, where expansion continues but slows, and everything gradually cools to near absolute zero over trillions of years. But if your passage destabilizes dark energy, you might trigger a localized Big Rip, a region of space where expansion accelerates uncontrollably, growing and consuming more space, spreading at light speed until it encompasses the entire universe. You'd essentially push a button that starts the countdown to universal disintegration. Alternatively, dark energy might decrease in your wake. If dark energy drops to zero or becomes negative, that region of space would stop accelerating its expansion. It might even start contracting. While the rest of the universe expands, this region would collapse back on itself, creating a contracting bubble within expanding space. What happens at the boundary between expanding and contracting regions? You'd have a discontinuity in the fundamental behavior of space-time. On one side, galaxies are moving apart. On the other, they're moving together. The boundary itself would be a region of extreme stress, where space is simultaneously trying to expand and contract. That stress might manifest as intense radiation, particle creation, or space-time fractures that spread along the boundary. Think of it like a crack in ice. The ice is expanding on one side and contracting on the other. The stress concentrates at the crack, and that crack can grow, splitting the ice into fragments. Your dark energy disruption might crack the universe itself, creating fragments that expand or contract independently, no longer connected by smooth space-time. The cosmic microwave background provides another angle on this. The CMB is the oldest light in the universe, released when the universe was only 380,000 years old. Before that, the universe was too hot and dense for light to travel freely. Photons were constantly scattering off electrons. When the universe cooled enough for atoms to form, photons were suddenly free to travel, and they've been traveling ever since. We can detect this ancient light from every direction in the sky. It's incredibly uniform. The temperature is the same to within 1 part in 100,000 no matter where you look. But there are tiny variations, tiny hot and cold spots that correspond to density fluctuations in the early universe. Those fluctuations are the seeds that grew into galaxies and galaxy clusters. The Cosmic Background Explorer satellite in the early 1990s, the Wilkinson Microwave Anisotropy probe in the 2000s, and the Planck satellite launched in 2009 have mapped these fluctuations in exquisite detail. They've told us the universe is 13.8 billion years old, that it's flat in its overall geometry, that dark energy and dark matter have the densities we measure. But the CMB is also still traveling through the universe. Those photons from the early universe are still out there, still crossing space, still carrying information from 13.8 billion years ago. When they pass through regions with gravitational fields, their energy changes slightly. They're gravitationally redshifted or blue-shifted. When they pass through hot gas, they gain a tiny bit of energy through the Sunyaev-Zeldovich effect. What happens when CMB photons encounter your light speed catastrophe? These ancient photons, traveling peacefully for billions of years, suddenly hit a region of infinite space-time curvature, infinite energy density, catastrophic field disruptions. They don't just scatter or get absorbed. At the energies involved, they might be converted into particle-antiparticle pairs. They might be blue-shifted to such extreme energies that they become gamma rays, capable of triggering nuclear reactions. They might be torn apart at a quantum level in ways that don't normally happen to photons. And this doesn't just affect individual photons. The cosmic microwave background is a coherent structure, a snapshot of the early universe that's been preserved in the light traveling through space. Disrupting it isn't just destroying photons, it's destroying information about cosmic history, it's erasing evidence of the Big Bang itself. Future civilizations, if any, survive your passage, would look at the sky and see regions where the CMB is simply gone. Patches of darkness where the oldest light in the universe has been annihilated. They might think those regions came from a different universe with a different history. They might conclude that the laws of physics are different there. They'd be partially right. Your passage would have rewritten those laws. Let's consider cosmic rays. These are high-energy particles, mostly protons, that zoom through space at nearly light speed. They come from supernovae, from pulsars, from active galactic nuclei. When they hit Earth's atmosphere, they create particle showers that can involve millions of secondary particles. Some cosmic rays are so energetic that we don't know what could possibly accelerate them to those speeds. The most energetic cosmic ray ever detected was observed in 1991 by the Fly's Eye experiment in Utah. It had an energy of about 3 × 10⁻20 electron volts. That's roughly the energy of a baseball thrown at 60 miles per hour, concentrated in a single subatomic particle. It was nicknamed the "Oh my God" particle because physicists couldn't believe anything natural could reach that energy. Your passage through space would make the "Oh my God" particle look like a slow-moving snail. Every particle in your path, every atom you collide with, would be accelerated to energies that make the most extreme cosmic rays look gentle. And these particles would shoot outward in all directions, creating a cosmic ray storm of unprecedented intensity. These accelerated particles wouldn't just be dangerous to life or matter, they'd be dangerous to the stability of space itself. When particles reach extreme energies, they can probe the fundamental structure of space-time. Physicists use particle accelerators to do exactly this: smash particles together at high energies and see what happens. The Large Hadron Collider at CERN accelerates protons to 99.999991% the speed of light, giving them energies of about 6.5 trillion electron volts. At those energies, we can create new particles that don't normally exist. We discovered the Higgs boson this way in 2012. We've produced tiny amounts of quark-gluon plasma. We've tested predictions of quantum chromodynamics and the standard model of particle physics, but we're still probing energies far below what existed in the first moments after the Big Bang. The particles created by your cosmic catastrophe would reach energies that haven't existed in the universe for nearly 14 billion years. At those energies, the separate fundamental forces, electromagnetism, the weak nuclear force, the strong nuclear force, might merge back into unified forces. We think this happened in the early universe when it was incredibly hot and dense. As the universe expanded and cooled, these forces separated into the distinct phenomena we see today. But your particle storm would recreate early universe conditions in isolated pockets throughout space. And unlike the early universe, where everything was uniformly hot and then cooled smoothly, you'd have sharp boundaries between normal conditions and extreme conditions. At those boundaries, the physics would be chaotic. Forces would be unified on one side and separated on the other. Particles would have different properties depending on which side they're on. What happens to an electron that crosses such a boundary? On one side, it's a normal electron with a specific mass and charge. On the other side, it might be part of a unified electroweak field where electricity and the weak force aren't distinct. Does it transform smoothly, or does crossing the boundary require a quantum jump, a discontinuous change that might be impossible? If crossing is impossible, you've created walls in space-time, regions that can't exchange particles or information because particles can't transition between them. The universe becomes fragmented into isolated zones that can never interact again. Each fragment would evolve independently, potentially developing different physical constants, different particle masses, different force strengths. Let's zoom down to the smallest scales and consider quantum foam. According to quantum mechanics, space-time itself fluctuates at the Planck scale, about 10 to the minus 35 meters, far smaller than an atomic nucleus. At this scale, the smooth fabric of space-time we perceive breaks down into a seething froth of virtual black holes forming and evaporating, space-time geometry fluctuating wildly, the very notion of distance and time becoming fuzzy. We can't observe quantum foam directly because it's so small, but it's a prediction of combining quantum mechanics with general relativity. Many physicists think a complete theory of quantum gravity, whether string theory, loop quantum gravity, or something else, will describe how quantum foam works in detail. But what does infinite energy do to quantum foam? The Planck scale is where quantum effects and gravitational effects become equally important. Below that scale, our current theories break down completely. Your infinite energy would pump enormous amounts of energy into quantum fluctuations. The virtual black holes that normally form and evaporate in tiny fractions of a second might become real, permanent black holes. The space-time fluctuations might amplify until they're no longer microscopic. They could grow to macroscopic scales. Imagine space-time at the quantum foam level becoming unstable. The smooth fabric that emerges from quantum foam fluctuations normally averages out to the predictable space-time we experience. But if the fluctuations amplify, they don't average out anymore. Space-time at larger and larger scales becomes unpredictable, fluctuating, unstable. You'd have regions where the geometry of space randomly changes from moment to moment, where distances aren't constant, where time doesn't flow smoothly. Nothing could exist in such a region. Atoms depend on electrons maintaining stable orbits at fixed distances from nuclei. If distances fluctuate randomly, those orbits become impossible. Matter would dissolve not because it's hit by something, but because space itself is too chaotic to support matter's existence, and this quantum instability might spread. Quantum effects can propagate through entanglement, through virtual particle exchanges, through mechanisms we don't fully understand. An instability in quantum foam in one region could potentially trigger instabilities in adjacent regions, creating a cascade that spreads through space like a quantum avalanche. Now let's consider whether the universe has any defenses against this catastrophe. Physics has conservation laws, fundamental rules that can't be broken. Energy is conserved, momentum is conserved, electric charge is conserved. These laws emerge from deep symmetries in nature, connections between different aspects of physics that mathematician Emmy Noether proved in 1915 must exist. Could these conservation laws somehow prevent the catastrophe? If you have infinite energy, where did it come from? Energy conservation says you can't create energy from nothing. So infinite energy appearing would violate conservation, which suggests the scenario is impossible, not just impractical or difficult, but fundamentally forbidden by the structure of physical law. This is reassuring, but let's push further. What if energy is being drawn from somewhere else? What if your infinite kinetic energy is borrowed from the gravitational field, or from the vacuum energy of space, or from some other source? In general relativity, energy conservation becomes complicated because gravitational potential energy isn't well defined in curved spacetime. You can have situations where local energy is conserved, but global energy is ambiguous. Could you exploit this ambiguity? Could infinite energy somehow be consistent with conservation laws if you account for all the subtle ways energy appears in relativity? Most physicists would say no. The infinite energy scenario violates not just practical limits, but fundamental principles. The universe enforces the speed limit for mass, not arbitrarily, but because exceeding it would require breaking laws that hold the universe together. But let's imagine for a moment that conservation laws somehow allow this, or that there's a loophole we haven't considered. Are there other mechanisms that might limit the damage? One possibility involves the holographic principle. This idea, emerging from black hole physics and string theory, suggests that the information content of any region of space is limited by the surface area of that region, not its volume. It's as if three-dimensional space is actually a projection of information encoded on a two-dimensional boundary. The holographic principle was inspired by black hole thermodynamics. Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, a measure of information content, is proportional to the surface area of its event horizon, not its volume. This was strange because entropy usually relates to volume. A gas in a container has entropy proportional to the container's volume. But black holes are different. Juan Maldacena's ADS-CFT correspondence, proposed in 1997, provided a concrete example of holography by showing that a gravitational theory in a five-dimensional space is mathematically equivalent to a quantum field theory on the four-dimensional boundary of that space. It's one of the most important results in theoretical physics in recent decades, connecting gravity and quantum mechanics in a profound way. If the holographic principle is correct, there are fundamental limits on how much information can be processed or stored in a region of space. Infinite energy might correspond to infinite information, and if you try to cram infinite information into a finite region, holography says you can't. Something has to give, that something might be the formation of a black hole. When you try to exceed the information capacity of a region, the region collapses into a black hole, hiding the excess information behind an event horizon. This would be a defense mechanism. The universe protects itself from information overload by creating black holes that quarantine the problem. But we've already discussed what happens when your infinite energy encounters black holes. The collision doesn't resolve the problem, it amplifies it. So even if holography limits information density, the limit is enforced by creating black holes, which then become part of the catastrophe rather than a solution to it. Another possible defense comes from quantum mechanics itself. The Heisenberg uncertainty principle says you can't simultaneously know a particle's position and momentum with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't about measurement limitations. It's fundamental to how nature works. When you try to localize a particle to a very small region, its momentum uncertainty increases. At extreme energies, this uncertainty becomes massive. Your light-speed object, carrying infinite momentum, would have enormous position uncertainty. From a quantum mechanical perspective, it wouldn't be localized to a specific point. It would be smeared across space in a probability cloud. But a probability cloud with infinite energy is still catastrophic. Instead of a point of destruction, you'd have a region of space where destructive probabilities dominate. Measurements would collapse the wave function into specific positions, but each measurement would release infinite energy at that point. You'd turn space into a quantum minefield where observation itself triggers catastrophic events, and quantum mechanics is probabilistic. If your wave function extends across space, there's a non-zero probability of finding you anywhere within that region. That means there's a chance, perhaps small, but non-zero, of your infinite energy manifesting at any point in space. The entire universe becomes vulnerable to spontaneous, catastrophic events as different parts of your quantum state collapse into reality. This connects to the quantum measurement problem. What counts as a measurement? When does a wave function collapse? These questions have puzzled physicists since the early days of quantum mechanics in the 1920s and 1930s. The Copenhagen interpretation says measurement collapses the wave function, but doesn't clearly define what measurement means. The many worlds interpretation says wave functions never collapse. Instead, all possible outcomes occur in different branches of reality. If many worlds is correct, your catastrophe doesn't happen in just one universe. It happens in all the branches where your wave function exists. You'd be destroying countless parallel realities simultaneously, creating an infinite multiverse catastrophe layered on top of the single universe catastrophe we've been describing. Let's shift perspective and consider what observers would experience during this catastrophe, not just the physical destruction, but the subjective experience of reality breaking down around them. Because physics isn't just about equations and particles, it's about what those equations mean for beings who experience the universe. Imagine you're an astronomer on a planet orbiting a star in a galaxy that's about to be crossed by our impossible light-speed object. You wouldn't see it coming. Light from the approaching catastrophe travels at the same speed as the catastrophe itself. There's no advance warning, no time to prepare, no chance to observe and understand what's happening before it arrives. One moment, you're studying the stars, perhaps pondering the mysteries of dark matter, or wondering if life exists on other worlds. The next moment, reality shatters. But what does that shattering look like from your perspective? First, there might be a flash. The infinite energy approaching you would blue-shift photons ahead of it to extreme energies. The ordinary starlight, the cosmic microwave background, even low-energy radio waves would be compressed into gamma rays and beyond. Your sky would suddenly blaze with radiation across all wavelengths simultaneously. If your eyes could process it before being vaporized, you'd see every direction at once light up brighter than any star, brighter than your sun, brighter than a supernova. But you wouldn't have time to register this consciously. The human brain requires about 50 to 100 milliseconds to process visual information into conscious perception. Neural signals travel at speeds up to 120 meters per second, incredibly fast by biological standards, but glacially slow compared to light speed. The destruction would overtake your neurons before they could fire. Your last thought would be interrupted mid-formation, synapses frozen in the act of processing information that will never complete. Would you experience anything at all? Or would existence simply terminate between one instant and the next, too fast for consciousness to register? There's something deeply unsettling about this. We imagine catastrophes as things we experience, even if only for a moment. The dinosaurs looking up to see the asteroid, people in Pompeii fleeing the eruption of Vesuvius, even victims of nuclear explosions in Hiroshima and Nagasaki had fractions of a second to perceive the flash. But this would be different. The universe around you would transition from normal to destroyed with no subjective experience of the transition. From your perspective, you'd be thinking your thoughts, living your life, and then nothing. Not death as we understand it, but cessation. The difference between existing and not existing, with nothing in between. For anyone farther from the direct path, the experience would be different, but no less horrifying. You'd see the effects before the catastrophe reached you. You'd watch stars suddenly vanish or explode. You'd see the fabric of space itself distorting, warping the constellations into impossible configurations. If you had sensitive enough instruments, you might detect gravitational waves of unprecedented intensity moments before the catastrophe itself arrived, those moments would be filled with incomprehension. Nothing in your experience, nothing in your civilization's scientific knowledge would prepare you for what you're seeing. The laws of physics as you understand them would appear to be breaking. Causality would seem to malfunction. Effect would appear before causes. Distant events would seem to happen simultaneously with local ones despite the light speed delay. Scientists in your civilization would scramble to understand. Theories would be proposed and discarded in minutes as new observations contradicted them. Some might realize the truth that reality itself is failing in those final moments. But what could they do with that knowledge? Who could they tell? What difference would understanding make when annihilation is seconds away? And what about consciousness itself? Human consciousness, as far as we understand it, emerges from the complex electrochemical processes in the brain. Neurons firing in patterns, neurotransmitters crossing synapses, networks of billions of cells creating the subjective experience of being someone, of thinking and feeling and perceiving. But consciousness depends on physics working normally. Neurons depend on atoms maintaining their structure. Neurotransmitters depend on molecular bonds staying intact. The electrical signals that propagate along axons depend on ion channels and concentration gradients maintained by the electromagnetic force. When the electromagnetic force becomes unstable, when atoms can't hold their structure, when space-time itself is fluctuating randomly, consciousness becomes impossible. Not just human consciousness, any form of information processing that depends on stable physical substrates would cease to function. Could consciousness exist in a fundamentally broken universe? Could there be forms of awareness that don't require stable matter or predictable space-time? This edges into philosophy and speculation, but it's worth considering. Some theories of consciousness, like integrated information theory proposed by neuroscientist Giulio Tononi, suggest that consciousness is a fundamental property of certain kinds of information processing, independent of the specific physical substrate. If that's true, then consciousness might be able to exist in different forms under different physical laws. Perhaps in a region where our physics has broken down, some other form of physics emerges, and that new physics might support information processing and therefore consciousness. But it wouldn't be human consciousness, it wouldn't be anything we'd recognize. It would be as alien to us as we would be to a two-dimensional being trying to imagine three-dimensional experience. More likely, consciousness simply ends where normal physics ends. The regions affected by your passage become dead zones, not just devoid of life, but incapable of supporting the kind of organized complexity that life and consciousness require. They become like the inside of a black hole singularity, where conditions are so extreme that no complex structures can exist, where entropy is maximal and information has no place to be stored or processed. Let's consider a more philosophical question. Does the universe have intrinsic value independent of conscious observers? If our catastrophe destroys a galaxy full of stars and planets but no intelligent life, does it matter? Some philosophers argue that value requires valuers, conscious beings, to appreciate or be affected by what happens. Without consciousness, the universe is just matter and energy following physical laws, neither good nor bad, beautiful nor ugly, important nor trivial. But others argue that complexity itself has value, that the intricate structures formed by galaxies and stars and planets represent something meaningful even without observers. The universe spent billions of years evolving from the smooth, nearly uniform state after the Big Bang to the rich tapestry of structures we see today. Destroying that structure, erasing that cosmic history, might be a loss, even if no one is there to mourn it. And there's another consideration: potential. A galaxy without intelligent life today might develop intelligent life in 1 billion years. By destroying it now, you're not just eliminating what exists, but foreclosing on what could exist. Every star you destroy might have harbored a planet where life was beginning. Every molecular cloud you vaporize might have eventually collapsed to form new stars and solar systems. You're not just ending the universe as it is, you're ending all the futures it might have had. The cosmic web, the large-scale structure of the universe, took billions of years to form. Tiny density fluctuations in the early universe grew under gravity's influence. Matter flowed along the cosmic web's filaments, gathering in nodes where galaxies formed. Empty voids expanded between the filaments, creating the foamy structure we observe today. The Sloan Digital Sky Survey and other projects have mapped this structure across billions of light-years, revealing the universe's evolution from simplicity to complexity. Your catastrophe would unravel that complexity. The structure built over cosmic epochs would be torn apart in moments. The universe wouldn't just lose its current state, it would lose the history encoded in that state. Future civilizations, if any, couldn't reconstruct what the universe was like by studying its structure, because that structure would be gone, replaced by chaos. This is a kind of informational death of the universe. Even if matter and energy continue to exist in some form, the information about how they were organized, about the history that led to that organization, would be lost. And in physics, information is precious. The second law of thermodynamics says entropy, disorder, always increases, meaning information becomes scrambled and harder to access over time. But the universe has been fighting that trend, creating local pockets of low entropy, organized complexity. Life itself is an entropy-fighting process. Living organisms maintain complex, organized structures by consuming energy and exporting entropy to their surroundings. Every cell, every organism, every ecosystem is a temporary island of order in a universe trending toward disorder. Your catastrophe would be the ultimate entropy victory, immediate maximization of disorder, instant conversion of organized complexity into formless chaos. Let's return to the physical realm and consider what happens in the long term. Assuming the universe somehow survives your passage, perhaps the damaged regions are limited, perhaps the destruction doesn't spread to encompass everything. What does the aftermath look like? The regions directly affected would be essentially reset to a state resembling the very early universe. Extreme temperatures, extreme densities, possibly a quark-gluon plasma, or even more exotic states of matter. Over time, these regions would cool and expand, recapitulating the early universe's evolution, but in isolated pockets surrounded by normal space. But the cooling wouldn't be uniform like it was in the actual early universe. The boundaries between affected and unaffected regions would create temperature and density gradients far steeper than anything that existed in cosmic history. These gradients would drive powerful flows of matter and energy. Shock waves would propagate outward from the boundaries. Turbulence would develop, mixing hot and cool regions in chaotic patterns. The normal processes of structure formation, gravity pulling matter together, clouds collapsing to form stars, wouldn't work in these chaotic conditions, or they might work differently, producing structures unlike anything in our current universe. You might get stars that form and collapse in thousands of years instead of millions. Galaxies that are denser or more diffuse than normal. Planets where the chemical composition is completely unlike anything in our solar system because the affected region had a different distribution of elements. Could life survive in such an environment? Life as we know it requires stability, predictable chemistry, reliable energy sources, moderate temperatures, a star that burns steadily for billions of years, providing consistent light and heat, a planet with a stable orbit, molecules that maintain their bonds long enough for complex reactions to occur. In regions devastated by your passage, none of these conditions exist. Temperatures fluctuate wildly. space-time geometry might still be settling, creating unpredictable gravitational fields. The elements needed for life, carbon, oxygen, nitrogen, phosphorus, might be present in completely different proportions than normal, or locked in forms that don't readily combine into organic molecules. But life is remarkably resilient. On Earth, we've found organisms thriving in boiling hot springs, in acidic mine drainage, in the crushing pressures of the deep ocean, in the dry valleys of Antarctica, even in the radioactive water pools of nuclear reactors. Tardigrades, microscopic animals also called water bears, can survive vacuum, radiation, extreme temperatures, and pressures that would instantly kill most life forms. They enter a state called cryptobiosis, where their metabolism essentially stops and they can remain in that state for years or even decades until conditions improve. Could some form of life adapt to the post-catastrophe environment? Not immediately. The initial conditions would be far too extreme. But over thousands or millions of years, as the affected regions cooled and stabilized, niches might emerge where complex chemistry could occur. And wherever complex chemistry is possible, life might find a way. It wouldn't be life as we know it. The different conditions would favor different biochemistries. On Earth, life uses DNA and RNA to store and transmit genetic information, proteins to perform chemical reactions, and lipid membranes to create cellular boundaries. But these are just one solution to the problem of self-replicating, evolving systems. Alternative biochemistries using different molecules, different solvents, different energy sources are theoretically possible. Science fiction has explored silicon-based life, ammonia-based biochemistry, life in liquid methane or liquid nitrogen, even forms of life based on nuclear reactions or plasma physics. Most of these seem unlikely in our universe because carbon chemistry is so much more versatile than the alternatives. But in regions where normal chemistry has been disrupted and reconstituted under different conditions, perhaps alternative biochemistries become viable. These alien forms of life, if they emerged, would evolve in environments utterly unlike Earth. Their biology would reflect those environments. They might perceive time differently if they exist in regions where time still flows irregularly. They might have senses adapted to detect space-time fluctuations or electromagnetic fields that vary unpredictably. Their metabolisms might operate on timescales much faster or slower than Earth life, depending on local conditions. And if they ever developed intelligence, their understanding of physics would be completely different from ours. They'd observe a universe where the laws of physics are more like rough guidelines, where consistency and predictability are local rather than universal. They might not even conceive of universal laws. They'd think of physics as something inherently contextual, varying from place to place. If they ever encountered our region of stable space-time, they might consider it bizarre. How can physics be so rigid, they might wonder? How can processes be so deterministic? Where's the variation, the chaos, the fundamental unpredictability that defines reality? To them, our ordered universe might seem sterile, oversimplified, perhaps even artificial. But let's consider a different question. What about advanced civilizations that existed before the catastrophe? Could any of them survive or escape? An advanced technological civilization, one with spacefaring capability, perhaps spread across multiple star systems, would have some warning, at least in systems away from the direct path of destruction. They'd detect the gravitational waves minutes to hours before the catastrophe arrived. They'd observe nearby stars vanishing or exploding. Their scientists would realize something unprecedented is happening. What could they do with that time? A civilization confined to a single solar system has few options. You can't evacuate billions or trillions of beings in minutes or hours. Even with fantastically advanced technology, moving entire populations requires time. The best they could do is preserve information, broadcast everything they know, everything they've learned, every piece of their cultural and scientific heritage, hoping someone somewhere receives it and remembers that they existed. But a civilization spread across multiple star systems might have a chance, at least partially. Star systems away from the catastrophe's path might survive if the destruction doesn't spread globally. Those outposts would endure, carrying forward their species and culture, even as their homeworld and other colonies are annihilated. Some civilizations might have developed technologies that could help. If they've mastered manipulation of space-time, perhaps they have warp drives or wormholes. They might be able to flee into alternate dimensional spaces or regions of space-time that the catastrophe can't easily reach. If they understand quantum mechanics deeply enough, they might be able to upload consciousness into quantum substrates that could exist in the extreme conditions. Science fiction has given us concepts like the Zeely sequence's human diaspora that eventually learns to encode minds in cosmic strings, or the culture civilization that stores consciousness in digital substrates, or transcendent scenarios where civilizations evolve beyond physical existence. These ideas are speculative, but they point to possibilities. If consciousness is fundamentally information processing, and if information can be encoded in forms other than biological neurons, then advanced civilizations might be able to preserve themselves in exotic forms that could survive what biological life cannot. But even the most advanced civilization is limited by physics. You can't outrun light speed, you can't violate causality, and you can't prepare for a catastrophe that arrives without warning at the speed of its own detection. The most likely outcome is that even advanced civilizations are destroyed, their last moments spent in frantic attempts to preserve some fragment of what they were, knowing those attempts will almost certainly fail. There's something profoundly tragic about this. Intelligence, consciousness, culture, these represent the universe's highest achievements. From lifeless matter through billions of years of evolution emerges beings capable of understanding the cosmos, of creating art and science, of asking why they exist and what it all means. And all of that can be snuffed out in an instant by a catastrophe that doesn't care, that has no malice or purpose, that simply is. This connects to the Fermi paradox. Enrico Fermi famously asked, "If intelligent life is common in the universe, where is everyone? Why haven't we detected alien civilizations? The galaxy is billions of years old. Even traveling at a small fraction of light speed, a civilization could colonize the entire galaxy in a few million years. So where are they? Many solutions have been proposed. Maybe life is rare, maybe intelligence is rare, maybe civilizations inevitably destroy themselves, maybe they're hiding. Maybe they're here, but we haven't recognized them. Maybe interstellar travel is harder than we think. But here's a darker possibility. Maybe the universe is more dangerous than we realize. Maybe catastrophes like the one we're describing, impossible though they may seem, have analogues that actually occur. Maybe there are natural processes or quantum fluctuations or cosmic phase transitions that can suddenly sterilize large regions of space. Maybe civilizations do arise, spread, flourish, and then are wiped out by phenomena we haven't discovered yet, because we've only been studying the universe scientifically for a few centuries. We know the universe has violent events. Gamma-ray bursts can sterilize entire regions of galaxies. Supernovae can render nearby star systems uninhabitable. Quasar jets beam enormous energy across millions of light years. Perhaps there are other, even more catastrophic events that occur, rarely enough that we haven't observed one yet, but frequently enough that they've eliminated countless civilizations over cosmic history. Your light-speed catastrophe is fictional, but it reminds us that the universe operates on scales and with energies that dwarf human comprehension. We exist in a narrow band of conditions, temperatures not too hot or cold, densities not too high or low, energy levels where atoms can exist and chemistry can occur. Outside that band, everything we know becomes impossible. Let's consider one more scenario. What if a civilization knew this catastrophe was coming and had centuries to prepare? Not just hours or days, but real time to develop countermeasures. Could physics offer any defense? They might try to create a shield, some way to deflect or absorb the incoming infinite energy. But what material could withstand it? Any matter placed in the path would be vaporized instantly. Electromagnetic fields would be overwhelmed. Gravitational deflection requires mass, and you can't create enough mass to deflect something with infinite mass. Perhaps they could manipulate space-time itself. If you could create a region of curved space-time that redirects the catastrophe around your location, like water flowing around a rock, you might survive. This is conceptually similar to how some theoretical warp drives work, not by moving through space, but by warping space so that distant points become closer. Miguel Alcubierre proposed a warp drive metric in 1994, showing that general relativity's equations permit a bubble of warped space-time that moves faster than light, while everything inside the bubble remains at rest relative to local space. The problem is that creating such a bubble requires exotic matter with negative energy density, which probably doesn't exist. And even if it does, the energy requirements would be enormous, perhaps equivalent to the mass energy of Jupiter or more. But a civilization facing extinction might attempt the impossible. They might pour all their resources into creating a space-time shield, even if the physics seems prohibitive. If they succeed, they'd exist in a bubble of normal space-time surrounded by chaos. They'd be isolated, cut off from the rest of the universe, but alive. What would it be like inside such a bubble? You'd see the boundary where your protected region meets the destroyed exterior. Beyond that boundary, physics doesn't work the way it does inside. Light might not propagate normally. Time might flow differently, or not at all. You couldn't send probes through, they'd be destroyed the moment they crossed the boundary. You couldn't receive information from outside. Nothing could cross into your bubble without being protected in the same way. You'd be in a permanent isolation chamber, a pocket universe of stability in a sea of chaos. Your civilization could continue, but only within that limited space. You could never expand, never explore, never interact with what lies beyond. You'd know that out there, somewhere, the universe continues, but you could never reach it. And over generations, what would happen to that isolated civilization? Initially, they'd remember what they saved themselves from. Stories would be passed down about the catastrophe, the brilliant scientists who devised the shield, the heroic sacrifices made to preserve their species. Their culture would be shaped by the knowledge that they're survivors, refugees in their own pocket of reality. But over centuries, over millennia, the memory would fade. The catastrophe would become mythology rather than history. Future generations might doubt it ever happened. How could anything destroy space-time itself? They might argue. The laws of physics are eternal and unchanging. This tale of cosmic destruction is just allegory, a story our ancestors told to explain why we live in this limited region. They'd develop their own physics based on what they observe inside the bubble. And that physics would necessarily be incomplete. They'd miss crucial phenomena that require interaction with the broader universe. They might conclude that their bubble is all that exists, that the boundary is the edge of reality itself. Philosophers among them would debate whether anything can exist beyond the boundary, and most would conclude it's a meaningless question. Beyond is not a place, they'd say. It's simply not place, the absence of existence. This is deeply ironic. By saving themselves, they've created a permanent prison. Their descendants might eventually possess the technology to breach the boundary, but doing so would mean instant death. The shield that protects them also condemns them to eternal isolation. It's a cosmic version of the monkey's paw. You get what you wished for, but not in the way you hoped. Let's zoom out one final time and consider the universe as a whole. Assuming the catastrophe doesn't destroy everything, assuming some regions remain intact, what does a universe scarred by this event look like billions of years later? The directly affected regions would have evolved into something utterly alien. Perhaps they've stabilized into a new kind of matter organization. Perhaps they remain permanently chaotic, dead zones where complexity can't develop. The boundaries between normal and affected space would be visible across cosmic distances, discontinuities in the cosmic microwave background, regions where galaxy clusters suddenly end, voids that aren't just empty but actively hostile to matter and energy. Future cosmologists in unaffected regions would study these scars and struggle to explain them. They'd propose theories, phase transitions in the early universe, collisions with other universes in a multiverse, quantum fluctuations amplified to cosmic scales. Some theories might be close to the truth, others would be wildly wrong. But without being able to study the affected regions directly, without being able to send probes that survive crossing the boundaries, they'd never know for certain. And they'd wonder, could it happen again? If such a catastrophe occurred once, what prevents it from happening somewhere else, sometime else? The universe would seem less secure, less fundamentally stable. Scientists would search for warning signs, for precursor events that might herald another catastrophe. Civilizations might build early warning systems, cosmic sentinels watching for anomalies. But what good is a warning when the catastrophe travels at the speed of light, when by the time you detect it, it's already arrived? This gets at something profound about the nature of physical law. We trust that the laws of physics are consistent and universal. An electron behaves the same way here as it does in a galaxy a billion light-years away. The speed of light is the same everywhere. Gravity follows the same equations whether you're on Earth or orbiting a black hole. This consistency is what makes science possible. We can discover principles in our laboratories and trust they apply throughout the cosmos. But what if they don't? What if physical law is more fragile than we think? What if there are conditions under which the familiar rules break down, not just in the extreme sense we already know about, black hole singularities, the first instant of the Big Bang, but in ways that could occur unexpectedly, catastrophically, without warning? Quantum field theory tells us that the vacuum, empty space, might not be in its lowest energy state. We might be in a false vacuum, a local minimum, rather than the true ground state. If that's the case, a quantum fluctuation could trigger a phase transition where the vacuum collapses to the true ground state. This is called vacuum decay, and it would spread at light speed, creating a bubble where the laws of physics are different. Inside the bubble, particles would have different masses, forces would have different strengths. Atoms, as we know them, might not be able to form. The phase transition would release enormous energy, destroying everything in its path. And like your catastrophe, it would arrive without warning. The bubble's edge travels at light speed, so information about it can't reach you before it does. This isn't science fiction. It's a genuine possibility that physicists take seriously. The discovery of the Higgs boson in 2012 allowed physicists to calculate whether our vacuum is stable, and the results are ambiguous. The best current measurements suggest we're either in a true vacuum or a metastable false vacuum that will eventually decay, but probably not for an incomprehensibly long time, far longer than the current age of the universe. But probably isn't certainty. There are error bars on those calculations. And even if the average time to vacuum decay is enormous, quantum mechanics is probabilistic. There's always a tiny chance it could happen tomorrow. We wouldn't see it coming. One moment, the universe as we know it. The next, a bubble of new physics expanding at light speed, destroying and remaking everything it touches. Your light speed catastrophe is, in a sense, an extreme version of vacuum decay. immediate and absolute rather than gradual and probabilistic, but similar in being an existential threat that travels at the speed of information itself, making defense or escape impossible. This brings us to the fundamental question: why does the speed limit exist? Why can't mass reach light speed? We can describe it mathematically. As velocity approaches light speed, mass increases toward infinity, requiring infinite energy to accelerate further. But why is nature structured this way? Here's one answer: the speed limit protects the universe from the very catastrophe we've been describing. If mass could reach light speed, the consequences we've explored, infinite energy, causality violations, space-time destruction, would be possible. The universe would be fundamentally unstable, vulnerable to exactly these kinds of catastrophic events. By making it impossible for mass to reach light speed, physics ensures these scenarios remain hypothetical. The speed limit isn't arbitrary. It's not just a cosmic speed limit sign that matter happens to obey. It's a fundamental protective mechanism built into the structure of space-time itself. In special relativity, the speed of light isn't really about light at all. It's the maximum speed of causality, the fastest rate at which cause and effect can propagate through space. Light happens to travel at this speed because photons have no mass, but the speed itself is more fundamental. It's the conversion factor between space and time, the constant that appears in the equation E equals mc squared, the speed at which all massless particles must travel. This speed limit creates a structure to space-time. It ensures that causality is preserved. Effects follow causes in a consistent order. It prevents paradoxes like the light-speed catastrophe we've described. It maintains the stability of the vacuum. It allows fields to propagate smoothly. It makes the universe comprehensible, predictable, governed by laws rather than chaos. Without the speed limit, the universe couldn't exist in its current form. Or perhaps it could exist, but only briefly, before random fluctuations or quantum events triggered catastrophes that unraveled everything. The universe would be violently unstable, constantly destroying and remaking itself in apocalyptic phase transitions. Our universe isn't like that. It's stable enough that stars can burn for billions of years, galaxies can form and evolve over cosmic epochs, life can emerge and develop complexity, intelligence can arise and wonder about the cosmos. All of this requires a universe that follows consistent laws, where the rules don't change randomly, where the fabric of reality is stable enough to support intricate structures. The speed limit is essential to that stability. By preventing mass from reaching light speed, it prevents the cascade of impossible consequences that would follow. In a deep sense, the speed limit is the universe's primary defense mechanism, the rule that keeps reality from tearing itself apart. This gives us a new perspective on why we can't travel faster than light, why warp drives and wormholes remain theoretical and probably impossible despite what science fiction suggests. It's not that the universe is being arbitrary or limiting our exploration, it's that breaking this limit would break the universe itself. When you feel frustrated that interstellar travel is so difficult, that even the nearest stars require decades or centuries to reach at sublight speeds, remember what we've explored here. The speed limit isn't a barrier imposed on us, it's a protective structure that allows us to exist at all. It's the reason there's a universe stable enough to contain stars, planets, and beings wondering why they can't go faster. And in the end, that's enough. We exist in a cosmos vast and ancient, full of wonders we've barely begun to explore. We can study distant galaxies, probe the nature of matter and energy, seek to understand the fundamental principles that govern reality. The speed limit doesn't prevent any of that. It just requires patience, something intelligent beings capable of asking these questions should be able to muster. The universe has structured itself in a way that permits complexity, stability, and understanding. The same rules that prevent light-speed catastrophes also allow for the gradual evolution of stars, the formation of heavy elements in supernova explosions, the emergence of planets where life can take root, and the development of minds capable of contemplating their own existence. That's not a limitation, that's a gift. The universe could have been a chaos where nothing persists long enough to be meaningful. Instead, it's a cosmos where cause and effect are reliable, where patterns emerge and persist, where intelligence can arise and understand the principles that created it. So when you imagine accelerating to light speed and the impossible catastrophe that would follow, remember that you're actually contemplating why reality works. The speed limit isn't what holds us back. It's what holds everything together. It's the boundary between the universe we inhabit, complex, comprehensible, full of potential, and the nightmare scenario we've explored, where physics breaks down and everything dissolves into chaos. We live on the safe side of that boundary. And that's exactly where we want to be. And if you made this far, I am sure you will love this other video at the left side of the screen. What you would see traveling at 1 light year per second across the cosmos. Discover how stars would shift into gamma rays due to extreme Doppler effects. Explore our stellar neighborhood in seconds and cross the entire Milky Way in just 28 hours, from Proxima Centauri to the Andromeda Galaxy and much more. See you there.